right, I'm just going to wait a couple of moments for people to drop on in, give people a chance to get the notification and say, hey, Tech Art Talk Live is starting. Quick, tune on in. Almost there. All right. So, okay, gang, let's get this show on the road. Welcome. It is 12:30. It is Friday. That means it's time for another episode of Tech Art Talk Live. My name is Chris, and I am going to be your host for today's session. Now, we've been going on a rant for a while of using HLSL in order to create various visual effects. Now, we created some other filters a couple weeks ago for some color management. Last week, we did it a little bit with some other things. And now this week, we're going to go on for various function filters, meaning that we are, instead of using something like a convolution filter like we did with last week, what we're going to do is go with something just a little bit more abstract, meaning like we're just going to perform an operation on the pixels in order to get them to behave and kind of do what we want with them. And so we're going to go through a bunch of things. Now, I didn't have enough time this week to prepare as much as I had wanted to, so we might have a little bit shorter of a session today, but I'm sure you're not heartbroken to hear that, but we will get this process going along right away, but we're going to start going on with our various post-process functions. Let's see. Okay, we've got it going. All right. Okay. Now, various function filters. I mean, like, there are an unlimited number of function filters. You can have any kind of function filter that you want. But what we're going to go over today is pixelization. And pixelization is a way of turning your world into Game Boy vision. Yeah, you know, that's basically the description of it. We pixelated it. And it also could use for distortion in order to kind of vary things up a little bit. We're not going to be showing any kind of distortion today, but distortion is what they used for, if you ever seen the movie Predator, yeah, that movie was one of the first times that distortion was used in order to get a character, and they actually distorted the background based on the pre-created character. So that was pretty cool. Now, another function that we're going to be going over is dithering. Now, dithering is when you're going to go for also another nostalgia look, but we're going to go back into the late 90s and so forth, when things like Microsoft only had a limited palette color range, and they made the most of the color range of what they could to do that. And we're not going to have enough time today, but I really wanted to get into edge detection. And so I think we're going to go into edge detection last week because it's a little bit more of an involved process, and I didn't have enough time to really prepare the process ahead of time. So we're just going to have to push that on to next week. So let's talk about pixelization. Okay, pixelization is a process that's used for blurring out portions of the screen with a mosaic-like pattern. They used to use it for censoring things, like if there was any kind of nudity, or if there was someone's face and they wanted to hide the face, they would put up the little pixelated bitmap right over the person's face, and that would obscure their vision. Or if there was like any kind of nudity, or if there was some kind of information that they didn't want to disclose, maybe like a license plate or something, then they would use a pixelization filter. All right, and so what's used for mostly today is reproducing that kind of like low resolution, nostalgic gamer's vision, kind of like a Game Boy. Okay, so it's very cool because this doesn't, I mean, it's a really, really super function, and it's really super easy, and it doesn't really involve anything with UVs. It doesn't involve any kind of thing. It's actually super simple, and in fact, you're going to kind of bang your head a little bit and say, man, why didn't I think of that before? All right, so the thing you have to be aware of, that there's one basic function or one basic formula that actually works with this, and that's this. Okay, there we have this fancy, colorful function, and the thing we got to know is we have some kind of variable. We're going to call it a p factor, and we're going to call it a pixelization factor. Now, this pixelization factor controls how much pixelization we want. Do we want a lot or we want a little? I don't know. It's controlled by the p factor. But then what we're going to do is we are going to grab the color of our pixel, and it's going to be, we're going to rearrange our UV coordinates. And we're first going to take the UV coordinates of every single pixel, and then we're going to multiply it by the p factor, whatever that is, and then we're going to take the floor operation. If you don't remember what the floor operation is, it's a mathematical function that when there is a fraction, it just kind of like removes the fraction part and takes the whole number portion of it. And that's a floor. And so we're going to take that screen position multiplied by the p factor, take the floor of that operation, and then we're going to take the floor of the p factor and then divide that through into the UV coordinates, and that's going to give us our new UV coordinates. And so that is all we're going to get, and that's all it takes to make a pixelization function. So I'm going to go ahead and go into my demo here and show you what we've got here. All right, so let me go ahead and grab this. Okay, boom, boom, boom. Oh, what I want? Okay, I want this one. All right, cool. All right, we've got our background here, and so what we're going to do is we're going to create a simple function. We're going to do it in blueprints, and then we're going to do it inside HLSL, because really this is supposed to be an HLSL lecture and not really the blueprints, but sometimes it's actually easier to see in blueprints. All right, so I'm going to create a new folder here, and I'm going to call this TATL demo. Okay, and then I'm going to drop into that. All right, so I'm going to go ahead and start things off by creating a post-process function, but it's really just a material. So I'm going to create a material, and I'm going to call it PP, and I'm going to call this PP. I'm going to call it BP for blueprints. Call it BP Pixelization. Pixelization. Yep, there we go. Okay, I'm going to drop into that. All right, here we go. Let me pull that over into here. Okay, there we go. Now, any kind of post-process filter that you're working with in UE4 always has to start with just a fundamental material. And then since we're using a post-process filter, it's actually going to follow the same progress over and over again. And then the first thing we got to do is click on this render node, and then we're going to change its material domain, and we're going to change it from surface, we're going to change it to a post-process. And things are going to go dark. And only the emissive color is that, because we only want an unlit thing kind of shining through. And in fact, since it's unlit, let's go ahead and change that shading model from default lit to unlit. It basically is redundant and kind of is going about the same thing, because any kind of post-process is unlit. Remember, we're rendering to a target render buffer, and then we're performing an operation on that target buffer and then sending it through the output again, just as a kind of a continuous reminder. And so what we're going to do is I'm going to grab something called a scene texture. And there we go. And this is where we're going to get this is basically our screen buffer. And so I'm going to change this to post-process input 0. And then the color is just going to go right into the emissive. Now, this is basically a pass-through filter, meaning like whatever we see inside that's been rendered to the render buffer is going to immediately get put through onto our post-process filter. So all we see is, well, what we see is what we get. We get a very WYSIWYG situation. So let's grab, we know that we're going to deal with our text coordinates, so let's go ahead and grab a text coordinate node. All right, so the first operation is we are going to multiply it by our p factor. And we don't have a p factor here, so let's create a scalar parameter. And then I'm going to call this a p factor, or pixelization factor. All right, so what we're going to do is we are going to multiply these two. And then we're going to take the floor operation of them. And just drop that into a floor. And once again, what that does is it rounds the resulting product of these two numbers down to a simple whole number. And then what we're going to do is we're going to take the floor of just the p factor, and then we're going to divide the resulting coordinates of our product, and we're going to divide it by the result of the floor of the p factor. And we're going to go divide. Okay, and we're just going to plug that into our UVs. And there we go. We have nothing left because we have a p factor of 0. But if we put this to something like, oh, I don't know, maybe 200, then you can see we get kind of a pixelated effect. If we make this number smaller, then it's going to be more pixelated, more chunky. And if we make it much larger, oh, maybe like 500, it's going to start to look a whole lot smoother. But you can still see the little jaggy edges around there. All right, so ultimately, let's see what this looks like. I'm going to hit save. And I'm going to change my p factor to something like 200, just so we know that it factors. In fact, let's change it to 150 so we know that we have something that we're dealing with. Yep. I'm going to hit save. All right. Now I've got to go into my demo level. Now what we're going to need for demo level is a post-process volume. So you got to have your post-process volume. And then what you're going to look for inside of the post-process volume is this parameter under rendered feature. You got to look at where it says post-process materials. And so you open that up, and then under that you see an array, and you have 0 array elements. That means there's nothing existing. So we're going to have to add one in there. And then it's going to access, it says choose. What are we going to choose from? Well, we only get one choice. We want as an asset reference, so we don't really get much of a choice. But here what we're going to do is we're going to grab our post-process material, and we are going to just drop it right into that slot. So here it is. I'm going to move that right into there. Come on. Okay, so what is this called? I'm just going to have to type that in. This is called PPBP Pixelization. So that should be easy enough to remember. Post-process volume. All right, here we go. Okay, this is PP_BP Pixelization. Whoa! And as we see, 150 is far too pixelated, and it looks totally unrecognizable. All right, now I could create a material instance and kind of modulate on the pixelization factor, but instead I'm going to do is create one more, a different material, but this one is going to be HLSL driven. And we're going to go through a very, very similar process. Oops, come on. There we go. I'm going to create a new material, and then I'm going to call it PP, just HLSL Pixelization. Pixelization. Yep, there it is. All right, I'm going to drop into that. All right, once again, we're just going to simplify this. We are going to make it a post-process material, make it unlit. All right, and so we're going to grab our scene texture. There, and then we're going to get our post-process 0. So that means right in from the frame buffer. Okay, now we're going to have our texture coordinate as input. We're going to go text coord. And then we're going to multiply this by our p factor. And so I'm going to create a scalar parameter. We're going to call that p factor. And then we're not going to do anything. What we're going to do is we're going to create a custom function. Now, if you remember a few weeks ago when we were working with our color mixing and our color blending, we created a custom variable, and in follow suit, we're going to create a new custom here. So we're going to go to custom node, and then we want just a plain old custom node, just like that. And let's see, what do we want to call this? We want to call this pixelization. Pixelization. Okay, for input, we are going to want, let's see, the output is we're going to want only a float 2. Why? It's because we're only going to be dealing with the U and the V coordinates. We're not going to be dealing with any kind of colors. We're just dealing with the U and V coordinates. And let's see, we want 2 inputs. we've got one input here, we got another input there. So let's make our first input our text coordinates. Text coords. And then our second, we are going to get our p factor. And I better call it right. I'm going to call it Pixelization factor. Okay. And text coords, okay, we've got that. And I'm going to change the name of this because you'll see why in a minute. So it's just text coordinate and pixelization factor. Okay, great. So let's go ahead and hook those up. We're going to put the results into here. And we're going to get an error. That's because we don't have any input hooked up. So let's put the texture coordinates into this guy and to this guy. And so, okay, what we have to do is, okay, once again, we have the whole picture, but we don't really have any function in there. So let's go ahead and add the actual code that goes ahead and drives this bad boy. And I'm just going to keep it nice and simple. I'm going to go ahead and plug this in here. Actually, what I'm going to do is I'm going to go over to Sublime, and I'm going to create a new file, and I'm just going to paste that right in there. So it's very, very simple. All we're going to do is take a float 2, and then from that float 2, we're going to get the texture coordinates, going to multiply it by the pixelization factor, and then we're going to take the floor of that operation. And then finally, we're going to take the that UV scale that we just computed, and we're going to divide that through the floor of the pixelization factor, and that's it. Voila. So I'm just going to copy this little function right from here and go back into my custom node. And I'm going to paste that right in there. And there we go. And we see that, once again, it turns to total white. But that's because our p factor is at 0. But we know it goes crazy ape nuts if we put a value of 150 in there. And, yeah, there it is. It's working. So let's go ahead and save this. And to really demonstrate the effectiveness of this, let's go bring this out. And then let's go ahead and change our post-process volume and change that to pp underscore pixelization. Okay, we'll grab that. All right, we've got that. So let's say pp pixelization. Oh, we want the pp HLSL pixelization. Ooh, there's a difference there. All right, there it is. We want that one. All right, not much difference. All right, so we're going to go and create a material instance from this post process. So I'm going to go ahead and create a material instance. I'm going to call it mi underscore HLSL pixelization. And then I'm going to bring this out here. Oops, that's not what I wanted to do. Got a little bit too excited. Yeah, there it is. I'm going to go ahead and drop this down right here. All right, so now let's go ahead and modify our post process. I'm going to call it mi underscore HLSL pixelization. All right, so now what we can do is expose our p factor, and now when we raise this up, we increase the number, it reduces the amount of pixelarity. Now something like right around 200 is probably like around Game Boy. If you really wanted to get pixelated and strange, you could drop it down to a value of around 100 and it really turns sketchy. But mostly if you want to try to kind of see detail and get into that kind of old pixelated view, you drop that down to about 200 to where you want to be. And that kind of changes the whole perspective on things. All right. Okay, so that is how we do pixelization. Now, the other thing I wanted to go over today was dithering. Now, what is dithering? Okay, let me get this. Hello, computer. Yes. Okay, it's an optical illusion. It's used to take advantage of eye blending of two colors that are in proximity to each other. So it's weird. If you have two colors, that one is yellow and the other one is green, if you put them close to each other and kind of overlap them, it kind of appears like they turn into orange. Well, some of the pixels are yellow and some of the pixels are green, but when they kind of like intermesh each other, they look orange. It's kind of weird, and it's kind of like an optical illusion, and this is what we're going to be duplicating. Okay, And this is also kind of good for achieving that 1990s 16-bit color graphics mode. You know, it's kind of like when there was only a limited amount of images, color space available for our graphics display. And a lot of times you also see it being used for transparency. Now, not so much because of the advancements of the GPUs, you really don't see, you really see true transparency. But in some of the older games, they used to use this dithering in a way of simulating transparency. All right, so if you look under this, we have these various examples. We have the toucans and the macaws, and then we have our multicolored cube. If we were going to pixelize them, then you can, or ditherize them, you can see that our cube has been ditherized, so we can see just an exaggerations of our big colors, and we see the exaggerations of our toucan and our macaw, but really our color palette has been dramatically reduced. Now, there's a cheap way, there's an inexpensive way and an expensive way of doing this. Okay, yeah, there's an example of what things were looking like in the 1990s with the old pixelization. Now, there's two ways of doing this, and a simple way of doing this is using something called a bare matrix. And a bare matrix looks like this. Voila! And so, basically, it breaks the screen up into little segments of, well, 4x4 tiles. And inside those 4x4 tiles, you're going to figure out where each pixel fits within that little 4x4 matrix. And then you're going to take that matrix, and then you're going to create some kind of number. And what that number is, I don't know. It depends on what it is. And you're going to take that number, and you're going to divide it by 16. Okay, great. What are you going to do with that number? Suppose that you're in a pixel, and the pixel lands on this spot, and it's 14. And so you're going to grab a number, and it's going to be 14 divided by 16. And you're going to do that for all four of these. And so what this does, this actually produces one of 17 various different patterns. And here are the various different patterns, where we're showing where we've got a gradation going from totally black to totally white and opaque. Well, this is what the 17 patterns would look like as it goes from totally black to totally white. You would see this dithering in between, and that's what we're going to simulate today. All right, so this is the algorithm. We're going to first sample a pixel, and then we're going to compute its illuminance value. Remember what we did a few weeks ago when we multiplied our color values by that 3 vector, and that 3 vector gave us what turned it into a grayscale value? That is ultimately what we're going to do again. We're going to figure out the grayscale value of our pixel value. Then we're going to calculate the position in the matrix that we were looking at earlier. And then we're going to compare the illuminance value against the matrix value. You're going to say, hey, wait a second. The result of that illuminance value is a 3 tuple. You know, it has red, green, and blue. But remember, it's grayscale, so that means the red, the green, and the blue channel all equal each other. So therefore, one channel, let's just say the red channel, is going to be equivalent to its illuminance value. But anyway, we're going to take the value of that red channel, and then we're going to compare it against the value against the matrix value. And ultimately, is one of two things that happen. If the illuminance is greater than the pixel value, then we're going to keep the pixel color. All right. If the illuminance now is less than the matrix value, then we're going to make the color black. And so we're going to be dithering between white, the normal color, and the black color. And so what this does is it kind of duplicates the actual dithering process. All right. And I think that's where I wanted to go. So I'm going to go and mix this up a bit. And I'll just go on to my demo here and move things along here. All right. Let me make sure that I've got my settings as expected. Boom, boom, boom. Okay, yep. I want this one over there. All right. So what we're going to do is we're going to create a new filter here. And so let's go ahead and create a new post-process. And I'm going to call this new material. I'm going to call it pp underscore bare dithering. All right, now I'm going to double click to go into that, and just as we did before, we are going to turn this into a post-process material. Click on material domain. We're going to make that a post-process. And our shading model, we're going to change that to an unlit model. And then we're going to start things off by going into a scene texture. Okay, so we've got our scene texture. Let's go ahead and put that into post-process 0. And then we've got that, so we're going to put that in there and then drop in there. Okay, and then what we're going to do is we're going to come across there. So what we're going to do is we got our scene texture, and instead of just going right into the emissive color, just like so, what we're going to do is we're going to put our function filter in between. We're going to create a new custom. There we go. And we're going to call our custom the bear filter. And then we're going to have, this one is going to output a float 4 because we actually are outputting color as it's coming from our render buffer. And then we are going to have 2 different inputs. Okay, so the first input, it's going to be our scene texture, just like we did for the other one. And the next one is going to be our matrix scale, because the matrix scale is going to control how big or large this little 4x4 tiling is going to be. And actually, it can make it smaller or larger, so we can control how much dithering is going to go on, and that's going to go and embodied as our matrix scale. All right, so I'm going to interject that. It's going to come into here, and it goes into there. Now notice that it's going to turn into, okay, we don't have a matrix scale, so let's create another scale, scalar parameter. And let's create one called matrix scale. All right, so let's give it a value. I think this one is basically smaller, so let's put the value of 0.5 into here. And voila, we get this, and it turns white. Why does it turn white? If we look over into our custom filter, we say the code here is that it returns a value of 1. Okay, so let's go ahead and throw some code in here. Now I'm going to show this what it looks like in Sublime, because it'll be easier to describe in Sublime than if we were going to do this in here. Now notice here that we're going to finish off by no, this is not what I wanted. This one's coming, so it's not quite yet. So I kind of got ahead of myself. There we go. This is what's going to be inside of our function. Well, first, what we're going to do is we're going to establish a constant integer, and we're going to have the scene texture ID. Okay, we're going to need that because what we're going to be doing is we're going to be reading directly from the render buffer. And the render buffer, in as far as UE4 is concerned, is ID number 14. And then we're going to get the texel size coming out of our render buffer. And then from UE4, we're also going to get the inverse of the texel size, which is 1 divided by the texel size, and we're going to take the floor of that. And then we're going to get the UV color by, we're actually going to get the texture coordinate, or the texture color of our unit. So this is going to give us our UV coordinates. And then from those UV coordinates, we're going to get our pixel color. Then what we're going to do is we're going to take and get our luminosity, or we're going to get the grayscale value. Notice all we're going to do is we've got the luminosity, and then we're just going to take the dot product of our pixel color, and we're going to multiply it, or dot product, against the luminosity, and that's going to give us our luma value. Then we're going to send it to our bare 4x4 function, putting in all those parameters, and then the result is going to be some kind of color value, and then we're going to multiply that color value either by a pixel color or 1. So ultimately, what's going to come out of this bare 4x4 function is we're going to either return 1 if our color value evaluates past the matrix, and it's greater than our illumination. We're going to keep it a value of 1, but it's less than our illumination. We're going to return black, and so therefore we're just going to multiply our pixel color either by 1 or by 0, making it either the pixel color, or we're going to make it black. But here's an interesting situation, and we go into this, and you'll see what the situation is in just a moment here. I'm going to go ahead and copy this and then drop this into my custom filter. Now when we go ahead and exit this, the UE4 is going to complain. It's going to say, hey, wait a second, bub, we don't know what bare 4x4 is. Okay, the way that the custom filter or the custom node inside UE5 is implemented, you can't inject any kind of actual function in here. You can't, it has to be contained within the little function as we created it as is. So in other words, what we have to do is we have to trick UE4 into letting us do something. And we're going to do that by we're going to create a new custom function. I'm going to drop that in here. And inside of that custom function, let's see. Let me go into and demonstrate what this is going to do. Why do we need this custom function? Because we have this thing and it's hooked up and we don't know where to go. I wanted to show you this a little bit. I forgot to show it earlier. But if you were going to go and look into the lit and go into, let's see, where is it? If we go into the Windows, let's see, hierarchy, home, preview state, high state, perspective, lit, show, background, okay. Oh, here it goes, window, come down here to shader code, and then choose HLSL code. All right, I'm going to copy this. And then I'm going to paste this right into here. Okay, now you see that we have this big mama huge 3,000 line shader, and actually this is the UE4 shader gang, and it's all right here. And how do I know this? Well, we actually put something in here earlier, and what do we call this? What do we call this function here? We called it our, we are looking for a bare 4x4, so I'm going to do a search for a bare. Okay, here is our code that we created earlier, and you'll notice that UE4 finished our function and it inserted this stuff right in here. So it created this float 4 called a custom expression, and inside of it, it comes in the various parameters. It returns the scene texture, and it comes in with the matrix scale. Okay, cool. And then we return the float 4, all the way through that we explained earlier. So what we want to do now is, instead of putting the code inside of the thing, what we have to do is kind of trick UE4 into letting us add more code. And we're going to do that with an extra custom node. What I was getting at. And here's our extra custom node. And let's see, how are we going to address this custom mode? And okay, I'm going to call this bare 4x4. Bare 4x4. I believe that's how we addressed it inside of the thing. As far as inputs, yeah, we don't want any inputs. So we're just going to hit that into the trash. So there's no inputs. And let's see, the output is, well, actually we're just going to leave that as is, right at float 3. And all we have to do in order to get this working is we have to just multiply our color by this new custom node and then plug it in here. Now this doesn't change anything, but it just makes the bare filter actually work, and it got rid of our error. And so we now have, there's a bare 4x4 function in there. So let's go take a look at what it looks like. I'm going to go to Window, and I'm going to go to Shader Code, HLSL code, and I'm going to copy that. And then I'm going to go back into my Sublime, and then I'm going to replace it. And then I'm going to go over, let's see. let's see, is it up here? Nope, I'm going to have to do a search for bear. Ah, here we go. All right, the custom expression 1. Okay, it is, let me say, let me go here. Okay, let me make sure we got that, and then let's make sure. I didn't quite get the shader code. All right, I'm going to go ahead and copy. And then I'm going to go ahead and paste this in here. Right. Okay, so it looks like, am I looking at this right? Okay. All right, no, that's something else that I was playing around with. Yeah, I was trying to get the probably filter. Okay, so ultimately what we have to do is we have to trick UE4 into tricking us, and here it is, and we have a new function here. Where is that? 21, 29, okay, yeah, there it is. Now notice that it begins with a return 1. So what we're going to do is we're going to append this, and then we're going to leave the return 1 right there where it is, and then we're going to insert new code in here. All right, now notice that we're going to create this new function, but we didn't finish it off with a closing. We didn't finish it off with a closing brackets. And why? It's because we got to stick with UE4's convention. But here's our function up here. So as input, we're going to bring in a float2 position, and then we're going to go and bring in the brightness. And so here's our position, and here's our brightness. And so what we're going to do is we're going to figure out our position within the 4x4 matrix. And we're going to get our x value for floor and the y value of floor. And we're just going to take our position.x, do a mod 4, position y, do a mod 4. And then we're going to multiply the x plus the y, multiply that by 4. And that's going to give us some kind of index. And it's going to tell us where within our matrix we're all sitting. And so there it is. There's all our values. And it's going to find out where we sit within the matrix. And then depending on where we sit in the matrix, we're going to get our limit value. So we've got 16 opportunities, and so we've got 16 values. But we also sent in the brightness. So here it is. So if the brightness is less than the limit that we calculated here, we're just going to return 0. So it means just return black. Otherwise, return 1. And there you go. Lo and behold, that is our bear function. So I'm just going to copy this one here from return 1 all the way to return 0. I'm going to copy that. And then I'm going to go into a bear 4x4 function and then paste that right into there. And let's see. Okay. All right. Okay. So I think I know what's wrong here. That this is not a float 4. This needs to be a float 4 in order to keep things nice. And there we go. All right. So here we can see that our image looks rather dithered. Let's go ahead and save this. And then I'm going to go back to my demo. And I'm going to create a material instance of my bear dithering. So I'm going to create MI. I'm going to call this demo bear. All right, so I'm going to go back to my post-process value, and I'm going to type in MI bear demo MI. So let's see which one is it? That was demo bear. Okay, that's the one I want. Yeah, there we go. You can see it's dithered already. But what we wanted to do is we wanted to change around this dithering value. So we've got the effect of dithering going on here. So let's go ahead and make a material instance out of that. Oh yeah, we got that. So let's see, mi deo bear. Okay, so let's go ahead and move it in here. So let's go ahead and modify that and play with its values. Okay. So now I'm going to just turn on my matrix scale. And now if you see, if I move over the matrix value, I can change it so it looks a little bit more coarser. You can see the actual position of our 4x4 tile. If we make it a little bit smaller, then it kind of like gets a little bit smaller, it makes it a little bit dinkier, and it kind of like brings up that dithering value right in there. And actually you can see the values as they appear, as they look a little bit more chunky as we bring down that number. And here it is looking really, really chunky. Okay, and so this is actually a lot of fun, and it can be used to give your game and your image a kind of a unique look and kind of give it that kind of a customization, more stylized feel that is if you were going to do it and just leave it by itself. All right, gang, that is what I wanted to go over today. And let me go ahead and change my view. Okay, so let's see. This week we talked about a post-process filter, but I didn't get around to creating edge detection, and I really wanted to get into edge detection. So I think I'm going to do is next week, I was going to go into shadow mapping, but I think I'm going to delay shadow mapping for just one more week and kind of like go into edge detection, because that's a real interesting topic. Okay, gang, we're all finished, and that's what I wanted to show you today. But if you liked what you saw, go ahead and press that little subscribe button down over in the menu. Or you can go check me out. My name is Chris Rhoda, and I am on Facebook and on LinkedIn. Or check out TechArt.edu, which supposedly is to recapitulate and cover all the shenanigans that of all the things that we do here at TechArt.edu and with TechArt Talk Live and all the Houdini stuff and all the books and so forth. So check it out on TechArt.edu. It's also on Facebook and on LinkedIn. And if you're really feeling brave, swing on by the TechArtEDU.com website. Go ahead and opt in. Give us your name, give us your email address, and we'll send you information as it arrives. All right, folks, thank you very much for your attention and your time today. And I look very forward to seeing you again next week when we deal with edge detection. And until then, arrivederci.